James Webb's hunt for distant galaxies keeps turning up surprises. Recently, astronomers' jaws hit the floor when our premier observatory aims its massive mirror and sensitive spectrograph at indeed incredibly old galaxy, dating to just 120 million years after the Big Bang. It is like someone had drained the lake, and the monster is sitting there at the bottom. And this galactic Nessie is not alone. So far, James Webb has turned up thousands of distant galaxies dating to the early universe, many more than astronomers had expected. Some of those galaxies are brighter, more massive, or more mature than astronomers would have thought. They are now scratching their heads, trying to explain how the galaxies could have grown up so fast. Join us as we dig deep into how James Webb just unveiled early the universe is different than we thought. To start, it's helpful to recall what the James Webb Space Telescope was built for. On Earth, astronomers often build telescopes on mountaintops and in remote deserts for an unobstructed view of the sky. But the Earth's atmosphere still mars the view. Space is the ultimate mountaintop, as NASA explains. James Webb launched in December 2021 as the successor to the Hubble Space Telescope, and it improves on its predecessor in several ways. For instance, because of its huge golden mirrors and infrared cameras, it can make better observations of planets orbiting stars other than our Sun. But for this discussion, what matters is how it can observe farther back in time than the Hubble telescope. In astronomy, the farther away an object is in a telescope's mirror, the older it is, because light needs time to traverse such large distances. Some of the light JWST captures is almost as old as the universe itself, dating back to 100 million to 250 million years after the Big Bang, the relatively infant days of our universe, which is believed to be 13.77 billion years old. That light is so far away, it has been traveling nearly the age of the universe to reach us. So, when James Webb focuses its mirrors on a particular patch of sky, it can see through time. The farthest objects in the image are the oldest. Those in the foreground are more current. The images that contain this rich history are called deep field observations. And while they appear in two dimensions to us, in them, scientists can see how the universe has evolved. Before James Webb, the Hubble Space Telescope gave humanity its deepest look into the evolution of space. And in the Hubble images, scientists saw a pattern. As they peered farther back in time, there were fewer and fewer galaxies, and they were smaller and smaller. This makes intuitive sense. Just like fossils in the oldest layers of the Earth's crust represent more primitive forms of life, the oldest galaxies in a deep field image ought to represent more primitive galaxies. And they differ from modern galaxies, because they had the shortest amount of time to assemble. They were like teenagers compared to the large adult galaxies of today. When James Webb went online, astronomers were eager to peer a bit more deeply into the past. They thought the pattern from the Hubble images would just continue, and we would maybe see a couple of more distant galaxies, but they would be very, very rare. However, that's not what James Webb found. When James Webb turned on, it was apparent that there was a lot more light back then and a lot more galaxies. Even though the galaxies appear to our eyes as smudgy blobs, scientists can study the quality of light coming from them and make inferences about their size and age. James Webb has found really mature, large, bright galaxies back even farther than we expected. And according to early analyses, many of these galaxies were apparently huge, full-fledged adults, not teens. To further the fossil metaphor, it would be like finding evidence of advanced life forms in layers of the Earth when life ought to have been just starting out. In more fun terms, it's like, at the earliest times, the universe was having a party, and we had no idea it was happening. Okay, you might be thinking, so what? We got big, bright, plentiful galaxies way back near the beginning of time. Unexpected, perhaps, but it's not like it's violating the laws of physics, right? Well, the problem is time. It's kind of like if you were flipping through a family photo album and came to the realization that your grandmother grew to be an adult from an infant in just a couple of months. Such a finding might make you wonder if we're missing a big piece of understanding human development. Or somehow, the pace of human development worked differently in the past. If these galaxies contain the number of stars implied by these early observations, it should be nearly impossible for them to exist. So, what explains these bright, large galaxies? We don't yet know. But the most extreme possibility is that scientists are missing a big piece in their understanding of cosmology. The best model we have for the evolution of the universe is the Big Bang. According to this model, the early universe was a place of extremes. It was inconceivably small and scorching. With all the energy and matter there would ever be crammed into a tiny space 1 billion times hotter than the center of the sun. In the first moments after the Big Bang, the universe cooled enough to allow fundamental particles, such as quarks and electrons, to spring into being. Quarks combined to form protons and neutrons, and not long after, the nuclei of deuterium, helium, and lithium were formed. Energy zipped around the infant universe in the form of photons, but that early light ricocheted off free electrons, which weren't yet bound to any atom at every turn. Fast forward another 380,000 years, and the universe had cooled enough to allow the early nuclei to pull in electrons and form neutral atoms. This is called recombination, although it actually marks the first time these particles combined. This moment ushered in darkness, a period we now call the cosmic dark ages. Looking at an object, either with our eyes or with a telescope, requires photons of light to hit some sort of detector, whether it's your retina or a camera. But the cosmic dark ages were a time when the universe was enveloped by a fog of neutral hydrogen that trapped the light of the first stars and galaxies. The fog didn't lift until 1 billion years after the Big Bang, when the neutral hydrogen had been reionized and once again split apart. Because light couldn't escape its surroundings during the dark ages, it couldn't journey outward through the universe to hit our detectors here on Earth, nearly 13 billion years later. As a result, trying to peer back at that time is like trying to see a light bulb through a thick, dark haze. But interesting things were happening, even if we can't see them. Think of our own dark ages here on Earth, between about AD 500 and 1000. It may not seem like much happened in terms of scientific or cultural advancement, but stirring beneath the surface were forces that would set in motion the Renaissance. Similarly, the cosmic dark ages were a time of great transformation. According to Avi Loeb, an astronomer at the Harvard-Smithsonian Center for Astrophysics, who was among the first to explore this time in the early universe, this period is special in the sense that it marks the transition between the universe being very simple and being very complex. Black holes, neutron stars, even life eventually here on Earth. The roots of it were planted at the Dark Ages. If we want to understand where we came from, that's where the story starts. Astronomers do know what the universe was like just before the Dark Ages began. That's because they have an actual image of what conditions were like at that time. When the first neutral atoms formed, the process released photons of light that set off across the universe, creating a cosmic snapshot of the exact conditions at the beginning of their journey. This cosmic microwave background radiation, also known as relic radiation, exists all around us today and tells astronomers that the universe was more or less uniform in density at that time, with only very small ripples in it. But those ripples are important. If you feed those perturbations into a computer simulation, you get objects like galaxies we see today. But the precise way in which that transition happened is still poorly understood. What astronomers do know with certainty, however, is why we can't see any light from objects shining during the Dark Ages. For starters, there wasn't much light before the first stars formed. Aside from hydrogen atoms, most of the universe was made up of dark matter, which doesn't emit light. What's more, a cosmic fog of neutral hydrogen atoms permeated the universe, scattering or absorbing many of the ultraviolet photons that the very first stars emitted. But the time it would take for a photon to escape the hydrogen was longer than the age of the universe. So light can't reach us from that time, however long we wait for it to arrive. But the Dark Ages didn't last forever. Astronomers believe that if they look far enough out into space, which means far enough back in time, they should eventually see where reionization occurs. This will be the boundary between the old, dark universe and the newer, transparent one. Key discoveries, such as the expanding universe through Hubble's observations and the Big Bang Theory's predictive success, have grounded our cosmic understanding in observable phenomena, revealing a universe that was once hotter, denser, and more uniform. Despite significant advances, the earliest moments and the fundamental cause of the universe's inception remain shrouded in mystery, perhaps forever so. As we try to push the reach of our theories to earlier times, we move up in energy from atomic and nuclear physics to particle physics. After all, the earlier you look at the universe, the hotter and denser it was, and so the particles that filled up space had higher energies. Thus, to dive deeply into the cosmic infancy, physicists must use concepts from high-energy physics, going beyond experimental results. With some confidence, we could push the clock back to 100,000th of a second after the bang, when the universe had energies comparable to those when protons and neutrons got broken down into a quark-gluon plasma, a state of matter that has been studied in the past 2 decades or so, with great success, but also with some serious conceptual limitations. However, we have good reason to believe that this state actually existed in the early universe, presenting a wall behind which matter was dissociated into its simplest known constituents. That is, before this, we can really talk about a primordial soup of elementary particles filling up space. The spectacular discovery of the Higgs boson in 2012 confirmed that we could study different forces of nature under the same framework. We know of 4 fundamental forces: the gravitational, the electromagnetic, and the strong and weak nuclear forces. The 2 latter forces are only active at subnuclear distances, explaining why we are not familiar with them in our everyday lives. What the discovery of the Higgs confirmed was that the electromagnetic and weak forces tend to behave in similar ways at very high energies, at the limit of what our current experiments can probe. If we map these energies to the early universe, we are talking about 1/1,000,000th of a second after the bang, or 10 to the power of -12 seconds. We don't understand exactly how particles interact at these energies, but what we do understand, summarized in the standard model of particle physics, indicates that the whole universe went through a sort of phase transition. This transition resembles the process where cooling liquid water crystallizes into ice, breaking the fluid's uniform symmetry, where molecules are evenly dispersed, into a rigid, ordered lattice. Similarly, we say that the universe went through a phase transition at about this early time when the electroweak force split into the electromagnetic and the weak forces. Details are missing, but that's the overall picture. At this juncture, cosmology hits a conceptual barrier, as it needs to navigate backward in time without experimental guidance. Despite decades of efforts across the globe, we have not gathered any information from the very early universe that could guide us. The solution, of course, is to extrapolate and propose models of the early universe that are compelling for different reasons. For example, they may offer explanations to current challenges to the Big Bang model, as in the inflationary model. They may open new avenues for research in very high-energy physics, as in theories of quantum gravity. Or they may inspire experimental work in novel directions, as in, for instance, searches for dark matter, and primordial gravitational waves. Inflationary models were proposed during the early 1980s as potential solutions to several issues plaguing the standard Big Bang model. For example, observations tell us that the geometry of space is very nearly flat, and we don't know why. We also don't know why the temperature of the microwave background mentioned above is so homogeneous, to 1 part in 100,000. We also don't know how the matter clumping needed to form galaxies and large cosmic structures originated. Somehow, matter gathered in various spots and attracted more matter. Inflation was proposed originally by MIT's Alan Guth to address these issues. To do so, it invokes a sort of Higgs-like field assumed to be part of some unknown particle physics model describing the physics of the very early universe. In the same way that the Higgs field drove the split between the electromagnetic and weak forces at 10 to the power of -12 second, the inflaton field drove the dynamics of the very early universe at 10 to the power of -35 second. That's a lot of zeros into the unknown. Guth's model, along with the many alternatives proposed since his pioneering work, rely on this extrapolation, assuming that a primordial field caused the universe to expand exponentially fast for a very short period of time. As the field loses energy, it relaxes to its lowest energy state and decays into a plethora of particles with explosive effectiveness, causing an ultra-fast heating of the universe. Some cosmologists call this the real Big Bang, though this is a matter of taste. One of the challenges here is to uncover an even earlier history of the universe, one that actually determines what kind of field this hypothetical inflation was and where it came from. Compelling as cosmic inflation is, we don't really have either a believable model nor any evidence that it truly happened, apart from concordance with current observations. A handful of models nicely describe the universe that we see: flat, homogeneous, crumpled up. But we still need a mother theory to give it more fundamental validity. What this theory might be requires even more adventurous extrapolations. Even if we assume that we can push back our models even further in time, we soon hit a monumental conceptual barrier. As we approach the highest energies that we can still make sense of, the universe may require a different way to be described, borrowing from quantum physics, the physics of the very small. The point is that in the quantum world, everything is jittery and everything fluctuates. If we carry this notion into the force of gravity and its relation to space and time, we need to consider the possibility that at very early times, there was no time and space as we know them, but some sort of vague quantum foam where space and time bubbled in different ways here and there, though here and there become very murky ideas. Unfortunately, our current attempts to describe such quantum spacetime foam in theories known as string theories and loop quantum gravity have been only partially successful or not at all successful, at least in providing a compelling scenario for the origin of the universe. We seem to be fundamentally stuck when it comes to the question of the origin of all things. And this is not surprising once we pay attention to the history of philosophy and the nature of science. The origin of the universe pushes the boundaries of what we can understand. It is one question where scientific and religious narratives sometimes get blurred. This is not because they approach the problem in the same way. Clearly, they do not. It is because the question being asked of both is the same. We want to know how everything came to be. We want to know because otherwise our story would be incomplete. We are creations of this universe, and the story of the universe is fundamentally our story too. There is no question that modern cosmology and astronomy have produced a remarkable narrative of the universe's early history. But can science really provide an answer? Like you and me, the universe has a birthday. We know that it started 13.8 billion years ago, and we can describe with confidence how the young universe evolved starting from 1/100th of a second after the Big Bang, although there are a few important gaps in the history we have yet to fill. That knowledge is a phenomenal achievement. But the question that lingers is how close to the source science can get. Current descriptions of the origin of the universe rest on the two pillars of 20th century physics. The first pillar is general relativity, Einstein's theory that gravity is due to the curvature of space caused by the presence of mass. The second pillar is quantum physics, which describes the world of atoms and subatomic particles. Combining the two is quite reasonable, given that in its infancy, the whole universe was small enough for quantum effects to be important. Current models of the origin of the universe, from string theory to loop quantum gravity to quantum cosmology to a universe that bounces between expansion and contraction, use the bizarre effects described by quantum physics to explain what seems to be unexplainable. The issue is to what extent they can truly explain the first cause. In the same way that a radioactive nucleus spontaneously decays, the entire cosmos could have emerged from a random energy fluctuation, a bubble of space that appeared from nothing, the quantity physicists usually call the vacuum. The interesting thing is that this bubble could have been a fluctuation of zero energy due to a clever compensation between matter's positive energy and gravity's negative energy. This is why many physicists, writing for general audiences, confidently state that the universe came from nothing. The quantum vacuum is that nothing, and proudly declare that the case is closed. Unfortunately, things are not so simple. This so-called nothing, the physicists' quantum vacuum, is far from the metaphysical notion of complete emptiness. In fact, the vacuum is an entity filled with activity, where particles emerge and disappear like bubbles in a boiling cauldron. To define the vacuum, we need to start from many fundamental concepts, such as space, time, energy conservation, and gravitational and matter fields. The models we construct rely on natural laws that have only been tested for situations far removed from the extreme environment of the primordial universe. The quantum vacuum is already a structure of enormous complexity. To use it as a starting point is to begin the story of the universe on the second page of the book. Our attempts to understand how the universe began require us to extrapolate what we know to energies 15 orders of magnitude above what we can test. That's 1,000 trillion times. We hope that things will make sense, and currently, we cannot predict that they won't. However, these predictions about the early universe are based on what we can measure with our machines and using current models of high-energy physics. Those models are also based on what we can measure and on what we consider reasonable extrapolation. This is fine, and it is the approach we have to take in order to push the boundaries of knowledge into unknown realms. But we should not forget what this theoretical framework rests on and claim that we know for sure how to conceptualize the origin of the universe. Mentioning the multiverse, stating that it is eternal, and concluding that our universe is a bubble sprouting from it, does not bring us any closer to a real answer. After all, it does not seem that science as it is formulated now can answer the question of the origin of the universe. What it can do is furnish models that describe possible scenarios. These models are excellent tools that we can use to push the boundaries of knowledge to earlier and earlier times, in the hope that observations and data will guide us further. However, this is very different from explaining the origin of life through complex chemistry. To explain the origin of everything, we need a science capable of explaining itself and the origin of its laws. We need a meta-theory that explains the origin of theories, a theory of everything. It is an overarching hypothetical framework that would explain the physics of the entire universe in a single equation. but unifying theories that define the large-scale cosmological structure of the universe with those that describe the minuscule quantum world of the subatomic particles has been a challenge for over a century. Figuring out such an all-encompassing theory was the dream of two legendary physicists, Albert Einstein and Stephen Hawking. But although equations that describe the universe on the largest and smallest scales have become more precise over the decades, they still don't unite to provide a complete picture of the physical world. The situation is so exasperating that some of the greatest physicists of today concede that they might not live to see it all fall into place. Hawking himself had given up on the search for a theory of everything before his death in 2018. Regardless, scientists keep looking for the missing piece of information that could plug the holes in a potential theory of everything. Experiments in particle accelerators such as CERN's Large Hadron Collider in Geneva, or observations of the most distant universe, may one day produce the breakthrough that generations of theoretical physicists have been waiting for. That breakthrough will most likely come from research into the nature of dark matter, the elusive, invisible substance that must make up about 85% of all matter in the universe to explain the gravitational behavior of galaxies and galaxy clusters. Astrophysicists, as well as particle physicists working with particle accelerators, have an idea of what they are looking for: a particle called axion, which is suggested as a candidate for dark matter particles and is, in fact, predicted by string theory. If they could somehow detect those dark matter particles or detect some signature of dark energy, the force driving the accelerating expansion of the universe, then that would start to really say whether the theory of everything is really something along the lines of string theory or whether it's something completely different. In addition, future missions, such as the European Space Agency's Athena mission, as well as next-generation particle colliders, may finally find the answer. But what will happen when all the pieces of the puzzle finally fall into place and we understand how our world works? Will that be the end of physics? Duff disagrees. After we learn the rules of chess, he said, we can finally start playing the game. Cracking the theory of everything will surely lead to a flurry of Nobel Prizes. But what comes next? We will have to wait and see. The best model we have for the evolution of the universe is the Big Bang. According to this model, the universe started as an infinitely dense, infinitely hot complex of space, time, matter, and energy. From these initial conditions came the expansion of space-time. This led to everything we see today: galaxies, planets, people, everything. While the Big Bang is a pretty grand idea, it still leaves us with a lot of details to unpack, starting from the universe's earliest stages, 1/zillionth of a second after expansion started, to the cosmos we see 13.8 billion years later. One detail astronomers have long puzzled about is who lit up the universe. How did this dramatic transition from darkness to light come about? And when James Webb peered back in time to obtain the sharpest data yet of this cosmic dawn, it provided insight into the universe's first billion years, shedding light on one of the universe's biggest mysteries, the period of reionization. Join us as we dig deep into how James Webb just unlocked the oldest secret of the universe. If you want to know what lights up the universe, the answer always depends on which wavelengths of light you're looking at it in. The universe is always illuminated by the cosmic microwave background, the leftover radiation from the Big Bang itself. Early on, this radiation was coupled to the plasma of ionized nuclei and free electrons, prior to the formation of stable neutral atoms. Less than 500,000 years after the Big Bang, neutral atoms formed, and this radiation simply streamed freely amidst the sea of atoms. But why wasn't this radiation blocked by the now intervening neutral atoms that populate the abyss of empty space? The reason is wavelength. It only streams freely through the atoms due to the fact that the cosmic radiation was much lower in energy than neutral, mostly hydrogen, atoms are capable of absorbing, at wavelengths too long for absorption to take place. If the radiation were higher in energy, atoms would not only absorb it, they would rescatter it in all directions, where it would be further absorbed by additional atoms. It's only because the radiation is so low in energy, it's primarily infrared light, that it can freely pass through the space that neutral atoms occupy. And the light-blocking effects of neutral atoms, so good at visible and ultraviolet wavelengths, but so poor at inherently infrared wavelengths, plays out not only in the very early universe, but in modern times as well. We see this even in our own galaxy. The stars and objects that persist in the Milky Way's galactic center cannot be seen in visible light. The dust and gas that are present blocks it, just as they efficiently block visible light all throughout the galactic plane. However, at longer wavelengths, infrared light goes clear through those neutral atoms. This explains why the cosmic microwave background doesn't get absorbed, but starlight does. Thankfully, the stars that form in the universe, particularly early on in cosmic history, can be massive and hot, where the most massive ones are much more luminous and hotter than even our sun. Early stars can be tens, hundreds, or even thousands of times as massive as our own sun, meaning they can reach surface temperatures of tens or even hundreds of thousands of degrees and brightnesses that are millions of times as luminous as our sun. These behemoths are the biggest threat to the continued existence of any neutral atoms that happen to be spread throughout the universe. What determines whether atoms remain neutral and capable of absorbing visible light, or whether they become ionized and transparent to the light that our eyes typically perceive? It's all about the energy of the radiation that strikes them. The key property of whether an atom becomes ionized by the nearby stars is that, for stars above a certain temperature, they'll emit some fraction of their light in the ultraviolet portion of the spectrum, energetic enough to ionize a neutral atom. And remember, at all moments in cosmic history, even today, the most common atom in the universe by number is hydrogen. More than 90% of the atoms present are still simply hydrogen. For a hydrogen atom in its lowest energy state, it takes a photon of 13.6 electron volts or more to ionize it, which very few photons emitted from most stars possess. But that's because most stars have their energy peak in either the visible or infrared portion of the spectrum, with fewer high-energy photons above a certain ultraviolet threshold. However, the hotter and more massive your star is, the more ionizing photons they produce. Because these are the shortest-lived stars, it's only within a few million years of forming a new burst of stars that you get an excessive amount of ionizing photons, which coincides with large numbers of hydrogen atoms being ionized. If you were to imagine a scenario in which all atoms inhabiting the universe became ionized, the depths of star-free space would be clear for light to travel through, meaning we could see the distant universe without a problem. All the starlight that was emitted would freely propagate through space, and none of it would be extinguished unless and until it arrived at the proverbial eyes of an observer. But even so long as a small percentage of the atoms remains neutral, that emitted starlight could be effectively absorbed, making it extraordinarily challenging to detect anything from the era of the first stars and galaxies. It's true that a smaller percentage of neutral atoms means that starlight must travel through larger numbers of them to be fully absorbed, as the extinction of light in astronomy is cumulative. What we need to happen, if we want the universe to become truly transparent to starlight, is for enough star formation to occur that it floods the universe with a sufficient number of ultraviolet photons to ionize the neutral matter in the intergalactic medium so that starlight can travel unimpeded. This requires a large amount of star formation and requires it to occur quickly enough that the ionized protons and electrons don't find one another and recombine again. The very first stars in the universe make a small dent in the population of neutral atoms surrounding them, but the earliest of the star clusters are small and short-lived. the universe will remain largely neutral with them alone, especially once the most massive of those stars die and neutral atoms reform. The second generation of stars, formed in the aftermath of the first generation's death, fare little better. The big problem is that these newly formed stars form in clumps and clusters of perhaps a few million solar masses at most. These early star clusters only have about 0.001% of the masses and numbers of stars found in the Milky Way, meaning that for the first few 100 million years of our universe, the stars within it are barely enough to make a difference in the neutral matter permeating all of space. But that begins to change when star clusters merge together, forming the first galaxies. As large clumps of gas, stars, and other matter merge together, they trigger a tremendous burst of star formation, lighting up the universe as never before. But note that the process of reionization is uneven and doesn't complete at the same rate in all locations and directions. On average, it takes 550 million years from the inception of the Big Bang for the universe to become reionized and transparent to starlight. We see this from observing ultra-distant quasars and ultra-distant galaxies. But because there are a few directions where the matter is reionized much earlier than average, it indicates to us that structure formation is uneven and gives us hope of finding early galaxies even before that 550 million year limit. Hubble uncovered one such galaxy, GN-Z11, whose light comes from an earlier time than the completion of reionization, just 407 million years after the Big Bang. However, other, more distant galaxies have since been discovered by James Webb that are invisible to Hubble's capabilities, as Webb's sensitivity to longer wavelength, infrared light, allows it to see features that are more difficult for neutral atoms to absorb. The universe becomes effectively transparent earlier at longer wavelengths when less reionization has occurred. Infrared eyes are what it takes to probe the epoch of reionization itself. At the most extreme cosmic distances ever probed, there are not yet galaxy clusters in the universe, and the first galaxies, which are largely to have taken shape between 200 and 250 million years after the Big Bang, cannot be revealed by visible light observations alone. But through the eyes of an infrared observatory, where the light is long enough in wavelength to not be absorbed by these neutral atoms, this starlight might shine through after all. So, it's no coincidence that James Webb was designed to look in the near and mid-infrared portion of the spectrum, all the way out to wavelengths of 30 microns, some 50 times as long as the longest wavelength light that human eyes can see. In fact, of the top 10 galaxies known at the end of 2023, 9 of the top 10 spots are James Webb galaxies, with GN-Z11, the sole confirmed galaxy not requiring either discovery or confirmation with the Webb telescope. The light, created in the earliest era of stars and galaxies, plays a cosmic role whose importance cannot be overstated, the role of making the universe transparent to all wavelengths of starlight. The ultraviolet light works to ionize the matter around it, enabling visible light to progressively farther and farther as the ionization fraction increases. The visible light gets scattered in all directions until reionization has gotten far enough to enable our best telescopes today to see it. But the infrared light, also created by the stars, passes through even the neutral matter, giving our 2020s array telescopes a chance to find them, even where no visible light is available. Once starlight breaks through the sea of neutral atoms, even before reionization completes, it gives us a chance to detect the earliest objects we'll ever have seen. It's no surprise that even in just its first 21 months of science operations to date, that James Webb has broken a slew of cosmic records, including records for most distant galaxy, most distant proto-cluster of galaxies, most distant black hole, most distant red supergiant star, most distant gravitational lens, and most distant quasar. The most distant reaches of the universe are slowly succumbing to our improved observatory, then bringing the previously unseen into view. And according to the latest observation, astronomers have used the Webb telescope and an effect predicted by Albert Einstein over 100 years ago to discover that small galaxies in the early cosmos packed a massive punch, shaping the entire universe when it was less than 1 billion years old. The revelations from this discovery are profound. Combined with the power of gravitational lensing, the Space Telescope was able to see some of the earliest galaxies. Among them were Lyman continuum-emitting dwarf galaxies, some of the faintest objects in the early universe. These findings are in a new research article led by Hakim Atek, an astronomer at the Institut d'Astrophysique de Paris, published in Nature, titled "Most of the photons that ionize the universe came from dwarf galaxies." Atek and his fellow researchers found 8 ultra-faint dwarf galaxies in the early universe. Contrary to previous thinking, these 8 galaxies were prodigious emitters of ionizing Lyman continuum radiation. Despite their apparent faintness, they emitted 4 times more ionizing radiation than previously thought. This helps cement their status as the objects responsible for the epoch of rayonization. As team member Irina Kamarinska of the Institut d'Astrophysique de Paris in France said, "This discovery unveils the crucial role played by ultra-faint galaxies in the early universe's evolution. They produce ionizing photons that transform neutral hydrogen into ionized plasma during cosmic reionization. It highlights the importance of understanding low-mass galaxies in shaping the universe's history." These dwarf galaxies were about 100 times less massive than the Milky Way. By using James Webb's powerful spectroscopy, astronomers were able to examine the light from these small, faint galaxies in great detail. The team of researchers realized that if there were enough of these galaxies, they could be responsible for the epoch of reionization. As each galaxy emitted ionizing radiation, it created a bubble of transparent hydrogen around them. These bubbles grew until they overlapped. Eventually, the hydrogen in the intergalactic medium was ionized and light could travel freely. While other sources like quasars and massive galaxies could have created their own smaller bubbles of ionized hydrogen, it was the smaller bubbles that allowed the universe to ionize more homogeneously. So, these dwarf galaxies made a large contribution to the architecture of the universe. According to lead author Hakim Atek, these cosmic powerhouses collectively emit more than enough energy to get the job done. Despite their tiny size, these low-mass galaxies are prolific producers of energetic radiation, and their abundance during this period is so substantial that their collective influence can transform the entire state of the universe. In the current age, we're only able to see other galaxies because of the rayonization. Without it, we'd be surrounded by opaque atomic hydrogen. So, discovering what made the galaxy transparent helps explain the universe we find ourselves in today. Scientists aren't done with this type of observation yet. While these researchers found 8 dwarf galaxies that can help explain the epoch of reionization, a more comprehensive picture of their population is needed to firmly establish them as the primary cause of the epoch of rayonization. An upcoming James Webb observing program called GLIMPSE will study dwarf galaxies in the early universe using the Webb telescope and gravitational lensing. Astronomers want to know how prevalent these early dwarf galaxies are so that they can further constrain their contribution to the epoch of rayonization. In short, with the great power of James Webb, we just have to keep looking, and eventually, we'll find out what's truly out there. While waiting for more and more groundbreaking discoveries made by James Webb, scientists has just stated that discovering highly unstable and explosive axion stars could help scientists finally shed light on the universe's most mysterious stuff, dark matter. Despite accounting for an estimated 85% of the universe's mass, dark matter remains effectively invisible because it doesn't interact with light. That also means it can't be made up of particles like electrons and protons that composes the atoms that come together to form stars, planets, moons, and our bodies. This has spurred scientists to search for the elusive particles that could indeed account for dark matter. One of the leading suspects for dark matter are called axions, light mass particles first theorized in 1977. New research suggests axions could be found if scientists look for regions in which the particles may have gotten clumped up. Potentially, such clumps may have created axion stars, with explosive results. As Malcolm Fairbairn, team member, a professor at King's College London, said in a statement, "Axions are one of the prime candidates for dark matter. We discovered that they have the capacity to heat the universe just like supernovas and ordinary stars after coming together in dense clumps. Armed with that knowledge, we know with far more certainty where to point our instruments out in the field to find them. Dark matter may not interact with photons of light, the particles associated with the electromagnetic force, but it does interact with one of the universe's other four fundamental forces: gravity. In fact, dark matter was discovered in the first place when scientists realized some galaxies are rotating so fast that the gravity associated with all the visible mass within them wouldn't be enough to hold them together. There had to be something else. Plus, in addition to discovering that dark matter is preventing galaxies from flying apart, scientists now believe that most, if not all, large galaxies are enveloped by halos of dark matter that extend far beyond their visible disks and halos of stars, gas, and dust. That means if dark matter is made of axions, these low-mass particles must exist in great numbers to account for such observed gravitational effects. It would also imply there are areas in which axions are densely packed. In those regions, axions would likely begin to act in unison as a result of the laws of quantum physics. This could cause large groups of axons at the heart of galaxies to form axion stars. However, the team says these axion stars wouldn't be as long-lived as the dark matter halos that surround galaxies. Axion stars, should they exist, would become unstable once they reach a certain mass. This would result in the stars exploding and releasing bursts of radiation. The team thinks this radiation may have heated gas that once existed between galaxies during the time period between the creation of the first atoms in the universe and the formation of the first stars, around 50 million to 500 million years after the Big Bang. The bonding of electrons to protons to create the first atoms during an era of the universe called the era of recombination also meant free electrons were no longer endlessly scattering photons. Thus, the universe suddenly became transparent to light, and this first light can now be seen in the form of a cosmic fusel that uniformly fills the universe, radiation called the cosmic microwave background. The team behind this research thinks explosions of axion stars in the early universe could have left imprints in the cosmic microwave background. Thus, searching for this signature, using radio waves known as the 21-centimeter measurement, could confirm the axion nature of dark matter. As Fairbairn explained, coherent axion stars, even those which are relatively compact, have the potential to burst into a halo of electromagnetism and light. Knowing the kind of structures axion dark matter can form and its impact on surrounding intergalactic gas can pave new ways for its detection. Being able to find the axion would likely help us solve one of science's biggest questions over a century in the making and help lay bare the history of the early universe. Calculating the number of axion stars that exist could ultimately reveal the full explosion potential of these unstable gatherings of dark matter and help explain how those explosions may interact with intergalactic gas. This will, in turn, give a hint at the size of the signal hiding in the cosmic microwave background. As King's College London researcher David Marsh said, 21 centimeter measurement is generally seen as the future of cosmology, and the part that it plays in the search for the axion is a large reason for that. There is currently a huge proliferation of axion searches being built, including projects like dark matter radio. It is a very, very exciting time to be an astrophysicist right now. The research on axion stars was published across a series of papers in the journal Physical Review D. In another interesting observation, scientists have just focused on the heaviest pair of black holes ever seen, weighs 28 billion times more than the Sun. Two supermassive black holes found in collision-created fossil galaxies are so massive that they refuse to collide and merge. And new discovery could explain why, although supermassive black hole mergers are predicted theoretically, they have never been observed in progress. The supermassive black hole system is located in elliptical galaxy B20402 +379. Together, the two black holes have a joint mass that is 28 billion times larger than that of the Sun, making this the most massive black hole binary ever seen. Not only that, but the binary components of this system are the closest in a supermassive black hole pair, separated by just 24 light-years. This is the only supermassive black hole binary that has ever been resolved in enough detail to see both objects separately. Curiously, while the proximity of the two bodies suggests they should collide and merge, they appear to have been locked in the same orbital dance around each other for over 3 billion years. The team that found the binary in data collected by the Gemini North Telescope in Hawaii thinks the supermassive black holes are being prevented from merging by their tremendous mass. As Raja Ramani, a member of the team and physics professor at Stanford University, explained in a statement, "Normally, it seems that galaxies with lighter black hole pairs have enough stars and mass to drive the two together quickly. Since this pair is so heavy, it required lots of stars and gas to get the job done. But the binary has scoured the central galaxy of such matter, leaving it stalled." That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time. As the James Webb Space Telescope continues its cosmic odyssey, the images of distant galaxies and potential supermassive black holes stand as testaments to humanity's insatiable curiosity. The telescope's transformative capabilities not only captivate our imagination, but also provide invaluable data for scientists worldwide. These awe-inspiring images serve as a reminder that the universe is a vast, dynamic tapestry waiting to be unveiled, and the James Webb Space Telescope is our window to the cosmic wonders beyond. In the beginning, there was a bang, Big Bang, if you will. This massive explosion created the universe and filled it with the seeds of all the matter and energy currently present. But with that kind of turbo kickstart, growth isn't something that ends after the initial blast. The universe continues to expand, even accelerating as it goes, at a rate referred to as the Hubble constant. The Hubble constant is an incredibly important number to pin down in the field of cosmology, but it's not an easy one to suss out. In fact, it's so difficult to divine that the Hubble tension caused by our inability to land on a single number has become arguably as famous as the Hubble constant itself. And recent results from the James Webb Space Telescope have just re-cemented this tension as a very real problem to overcome. If a researcher wants to estimate the Hubble constant, they have two main avenues. There are others, of course, but the two most common are Cepheid variables and the cosmic microwave background. The cosmic microwave background is the leftover radiation still permeating the universe from the Big Bang. Using the cosmic microwave background is often likened by researchers to using a baby picture to predict what someone will look like as an adult. To some extent, knowledge about the universe's infancy should allow researchers to make predictions about its current state. Researchers have long used it to make inferences about the very beginnings of our universe, and have used it to predict what the Hubble constant should be. Fairly recent cosmic microwave background calculations set the Hubble constant at around 68 kilometers per second per megaparsec. But the thing about theory is that you need to test it, and when the Hubble telescope launched, it became possible to do just that. Free of the constraints of ground-based telescopes clouded by atmosphere, the Hubble telescope was able to take extremely accurate distance measurements of far-off objects. And that's where Cepheid variables come in. Cepheid variables are a type of pulsating star that falls into a category of objects called standard candles. Objects that have a measurable and consistent brightness, allowing us to fairly straightforwardly measure how far away they are. Measuring distances isn't easy in space, but it's crucial to being able to measure expansion. As convenient as it would be to stop there, there's one more step to the Cepheid method. Once their brightnesses have been divined and we know how bright a Cepheid is that blinks at a certain rate, we use those brightnesses to calculate the brightnesses of nearby supernovae. Then, using a quality called redshift, we use those supernovae to calculate the brightnesses of other supernovae that are even farther away. Because they're much brighter, we can see supernovae at much greater distances than we can see Cepheids. And because you can see the expansion of the universe better the further away you look, we look to the far-off supernovae for the ultimate calculation. This chain of brightnesses is referred to as a distance ladder. And you can't move to one rung without first calculating all the ones that come before. Over time, the Hubble telescope clocked distances for several Cepheid variables, the first rung on that distance ladder, which in turn allowed researchers to make an experimental measurement of the Hubble constant. But instead of agreeing with the prediction, it came out totally different: 73 kilometers per second per megaparsec. When experiment and theory diverge, it can mean one of two things: either your measurement is wrong or your theory is wrong. And that, in a nutshell, is the Hubble tension. Which is wrong, the theory or the experiment? That is where James Webb can help. By observing in the infrared spectrum, it will be able to look straight through pesky clouds of space dust that all too often interfere with local astronomers' measurements. The Hubble Space Telescope, the previous tool of choice for local astronomers, has far more modest infrared capabilities. Its infrared measurements come at the expense of lower image quality. But James Webb can do both: observe in infrared and maintain high-resolution imaging. Crisper, dust-free images. That Webb promise. The telescope is such a technological improvement that scientists expect its unprecedented infrared measurements might at last bridge a growing rift between astronomers over how fast the universe is expanding. And in a remarkable observation, the telescope took images of the same stars as the Hubble telescope and calculated a very similar Hubble constant. Although the Planck number disagrees from Hubble and James Webb number by less than 10%, the discrepancy in the measurements implies that there's something terribly wrong with our understanding of the universe. Unless an error turns up in one of the measurements, it will take strange new physics to explain the tension. As cosmologist Adam Rees of Johns Hopkins University, papers in the literature over the last 10 years have invoked anything from weird dark matter to weird dark energy, to another exotic particle, to a magnetic field in the early universe, to a new field, all kinds of things. Some of these explanations look semi-successful, some of them look like failures, some of them would cause other problems. Developing a theory that might resolve the tension is still very much in the skunk works or extremely speculative stage of trying to understand what the tension could mean. Like the Hubble telescope, astronomers using James Webb calculate the Hubble constant by observing flashing stars known as Cepheid variables. As told, combining distance and speed observations of Cepheid stars leads to a measure of the expansion of the universe. But Cepheid variable stars tend to sit deep inside galaxies, surrounded by crowds of other stars. That can make it difficult to get good measurements of the Cepheid's speeds and locations. One simple resolution for the Hubble tension could have been that the Hubble telescope measurements were simply off. Enter James Webb, which can peer through the stellar crowds to clearly make out the color and brightness of Cepheid variables. The higher resolution Webb images provide data with dramatically lower uncertainties and reduced confusion with nearby stars than the Hubble telescope could manage. The result? The Hubble telescope measurements have been right all along. This study alone isn't enough to convince astronomer Wendy Friedman of the University of Chicago. The two galaxies studied are comparatively close to us, on cosmic scales, with the farthest one about 75 million light-years away, she notes. The relative proximity makes it easier to pick out the Cepheids from the stellar crowds. Friedman suspects it will be harder to distinguish Cepheids from the crowds of surrounding stars in more distant galaxies, even with James Webb. If so, Rees's confirmation of the higher Hubble constant may crumble with analysis of more distant Cepheids. Hints that the measurements might hold up at larger distances arose in S' presentation at a conference in Baltimore dedicated to the first year of James Webb science. Rees showed preliminary Cepheid data from 4 more galaxies. One of them is 140 million light-years away, among the most distant galaxies in the Hubble telescope Cepheid studies. Webb data from those stars also line up with the Hubble telescope measurements. Although still awaiting peer review, the images strongly suggest that James Webb has indeed overcome the uncertainties that resulted when light from Cepheids got mixed up with light from nearby stars in the lower-resolution Hubble telescope images. University of Cambridge astrophysicist George F. Stathiou, who was not involved in the study, is both convinced that Rees has gotten the measurements right and confounded by the implications. F. Stathiou is a member of the Planck satellite collaboration, which studied the oldest light in the universe, called the cosmic microwave background, and found the lower value for the expansion of the universe. The satellite's calculation is based on images of the patterns in light from the early universe. Together with the standard model of cosmology, the images show that the universe is expanding with a Hubble constant that's lower than James Webb measurement by about 5.6 kilometers per second per megaparsec. As it stands, there doesn't seem to be anything wrong with the Planck measurement of the Hubble constant or with Webb observations. The tension between the measurements points a finger at the standard model of cosmology as the problem. But the standard model also appears to be unimpeachable. It's withstood numerous other challenges without breaking down. The model came about in part due to the discovery of the accelerating expansion of the universe, which earned Rees and others a Nobel Prize in physics. The revelation was a key piece in shaping the model to include dark matter, dark energy, and other factors, making it the simplest theory that can accurately describe the universe. After all, we know that there's still more to learn. This is a crack or a surprise that doesn't fit. Put simply, there's a problem with the standard model. We can revise it, but we don't know how to revise it, which direction or in what way. But note that we also can't rule out the possibility of completely new physics. According to Friedman, if there's new physics, that'd be fun. We'd all like to see something new and interesting. Either way, I think it's going to be an exciting result, either confirming the standard model or showing that there's something still in the model that's missing. Regardless of the final result, scientists still expect James Webb to find it. A silver lining, astronomers observing the galaxy MRG M0138 with the James Webb telescope have discovered a second type UI, a supernova in the distant galaxy. The first supernova was nicknamed Requiem. This second supernova has been called Encore. MRG M0138 is the most distant galaxy to be seen with two-type Ia supernovae, and in fact, That's very important for helping to solve what is possibly the greatest puzzle in cosmology right now. However, there's a catch. While most of the images of the two supernovas have appeared, one of the light paths is predicted to be much longer, based on models of the distribution of dark matter in the Lensing cluster. Those phenolimages are not expected to appear until the mid to late 2030s. While the aging Hubble Space Telescope might not still be active in 2035, hopefully James Webb will still be. If it is, and if it can detect the appearance of the final images from Requiem and Encore, the measurement of the Hubble constant that they provide could help settle the matter of whether so-called Hubble tension is merely experimental error or a real phenomenon. Back on Earth, astronomers have long wondered how Earth became water-rich, bountiful with abyssal oceans, frigid glaciers, and rain that pours from the sky into lakes, rivers, and wetlands. Water, which is composed of the first and third most common elements in the universe, is a deceptively simple molecule to form. However, while the details of its delivery to rocky planets like our own may be essential for understanding life,